Definition. If f is a function of two variables like x and y, then we can define the gradient of f, which is basically a vector function denoted by nabla f or gradient of f, defined as the gradient of f of x and y is, please pay attention to the symbol that we're using. It represents a vector. The very first component of the vector is partial derivative of f with respect to x. We use a comma to separate it, and partial derivative of f with respect to y. You can also represent this using another vector notation, partial derivative of f with respect to x, or the rate of change of f with respect to x in the direction of x-axis, represented by I, plus the rate of change of f with respect to y in the direction of y-axis, and j representative of y-axis. Example for you. Consider the following function. If f of x and y is sine x plus e to power xy, then to find the gradient of the function, we're going to find the partial derivative of f with respect to x. The partial derivative of this function, it includes two other functions inside of it, sine x and e to power xy. The derivative of sine x with respect to x, as you know, is cosine x. For e to power xy, we're going to apply chain rule. The derivative of e to power xy with respect to x is y e to power xy. So we can form some portion, some part of the gradient of f, which can be written as cosine x plus y e to power xy. So we copy down the cosine plus we copy down y e to power xy. Now for the second portion, we need to find the partial derivative of function with respect to second variable y. The function is sine x plus e to power xy. So in taking the derivative of sine x with respect to y, it doesn't have any y in it, so you're going to get 0. But for e to power xy, the derivative with respect to y is x e to power xy. And as I mentioned, the derivative of sine x with respect to y is 0. This guy basically acts like a constant. So now you can write down the second part of your gradient, which is x e to power xy. If I ask you to calculate the gradient of the function at a specific value, now that you have your vector function, you just need to do the substitution. You plug in 0 for your x, and then 1 for your y. You get 2 and 0. So that's how you calculate the gradient of a function at a specific point. Another example for you. Our goal is to find the directional derivative of function x squared y cubed minus 4y at the point 2 and negative 1 in the direction of a given vector with components 2 and 5. First, let us compute the gradient vector at the point 2 and negative 1. To find the partial derivative with respect to x, we treat y and y cubed as constant. So take a look. The partial derivative with respect to x of the function x squared y cubed minus 4y is 2x y cubed, and this guy just 0. So the gradient function is 2xy cubed in the direction of x-axis plus, let us take the derivative with respect to the second variable y, and here you have x squared y cubed minus 4y. The derivative with respect to y becomes 3, this is the exponent, goes in front of x squared times y to power 3 minus 1, or y squared minus the derivative of 4y is just 4. So the rest of your gradient function is 3x squared y squared minus 4 in the direction of y-axis. Now, since we want to calculate the gradient at the specific point 2 and negative 1, we just need to do the substitution. Here, if I plug in 2 for my x and negative 1 for my y, I get negative 4. So you have 2 times 2 and negative 1 to power 3, which becomes negative 1, so you get negative 4 back. Now, for the partial derivative of f with respect to y at point 2 and negative 1, you just plug in 2 for your x and negative 1 for your y, and it becomes 12 minus 4, or 8. Very good. So the gradient of the function at 2 and negative 1 is negative 4 and 8. Note that vector v is not a unit vector, but since we can calculate the magnitude of this vector, the vector 2 and 5 has magnitude square root of 2 squared plus 5 squared, which is 4 plus 25, or square root of 29. Now, if you divide each component of the vector by the magnitude square root of 29, you basically create a unit vector. The unit vector, denoted by u, is vector itself divided by its magnitude, or 2 divided by square root of 29 in the direction of x-axis, plus 5 divided by square root of 29 in the direction of y-axis. As you remember, the directional derivative of function f in the direction of vector unit vector u is the dot product between the gradient of the function and the unit vector. This is the formula that we introduced before. Now, the directional derivative of function f at point 2 and negative 1 in the direction of unit vector u is the dot product between the gradient of f at 2 and negative 1 and dot product with unit vector u. We calculated our gradient to be negative 4 and 8, and this unit vector is 2 divided by square root of 29 and 5 divided by square root of 29. Now, if you do the dot product, it means that you're multiplying the first components, and then you multiply the second components, add them together, you get 2 times negative 4, which is negative 8, plus 8 times 5. So you get 32 divided by square root of 29. So the directional derivative is positive. It means that in the direction of this vector, we have a positive rate of change. It means that we see an increase as the rate of change of the function in this direction.